Hi everyone, my name is Zihui Wang. I will be presenting our design for Team 21. Our topic is the adoption of additive manufacturing technologies in aircraft wings. I will start off with the background. Globalization has been impacting the world in the last few decades. One of the impacts brought by globalization is the increasing demand for air transport. However, there are several existing shortcomings in the traditional machining. First, building an aircraft requires approximately 50 weeks of manufacturing lead time. Second, the traditional machining process uses solid materials with high density, which results in a very heavy aircraft structure. From research, we found out that additive manufacturing has been introduced to the aerospace industry in recent years. Aircraft company like Boeing has already adopted laser-based 3D printing technology to print small aircraft parts. However, there are two big problems. One is that it can only print small parts, and second is that it can only print parts with simple geometry. To address these two problems, our team adopts additive technology used in construction industry to aircraft manufacturing. In the construction industry, they use directed energy decomposition method as the solution to 3D printing large buildings. The metal used for additive construction are also commonly seen in the aircraft industry. So the main focus of our design is to use additive manufacturing technologies into the manufacturing process of aircraft wings, which is the second longest part of an aircraft. There are two materials for the DED method, which are the metal powder and the metal wire. Comparing the two materials, using powder can yield higher resolution and thereby results in a more accurate shape of the final product, lower machining costs, as well as less material waste. So for our proposed design, we use metal powder as the printing material. To implement the large-scale DED technology in the design, a multi-degree of freedom robotic arm is required for the installation of nozzle and the material feeder. A high-energy laser or electron beam will be installed to melt the extruded material. A large CNC machine is required to ensure the large printing size of the component. The method also has some benefits. It has high production rate, and since the operation of the large-scale DED does not require a flat surface due to the working principle of the technology, it could be further used for the purpose of parts maintenance and repair. Here we did some comparison of the three manufacturing methods. I'll be focusing on the existing 3D printing methods versus the DED methods. We can see for the cost, so when we're comparing the existing 3D printing technology with the DED method, so for Boeing 747 aircraft, the wing weighs approximately 40,000 kilograms. So by calculation, the manufacturer can save up to 25% of the material cost. Looking at the lead time, DED method has higher production rate. Its material decomposition rate is 3 to 9 kg per hour, while SLM and the EBM 3D printing method only has 0.1 to 0.2 kg per hour. The DED method also has higher accuracy in terms of when printing the layers. The accuracy for traditional 3D printing method is plus or minus 0.3 mm, while the accuracy for DED method is plus or minus 0.1 mm. So to sum up, the DED method has lower material cost, higher production rate, and higher accuracy. Next, I will walk through the design process in detail. The very first step of the manufacturing process is to create a 3D CAD model for the component. The model will be analyzed by computer and sliced into layers prior to the general printing process. The next step is the metal powder production. Gas atomization is widely used for the production of metal powder. As you can see in the figure 3, the metal is first melted into liquid and stored in the feeder. As the liquid metal is extruded out, it's disrupted by a stream of high-pressure gases such as nitrogen and argon. The atomized droplets of the metal are then solidified in the atomizing chamber. Once the desired metal powders are ready for supplementation, they are then dried in a furnace and transferred into a powder feeder of the DED system. Looking at figure 4, it shows the general process of DED method. As the metal powders are deposited, the energy-intensive laser beam melts the powder instantly to form the melt pour onto the workpiece. Argon is normally used in this process to provide the shading purpose. There are two very important parameters, which are the linear heat input and the powder feed rate. They are used to ensure that powder provided by the laser is sufficient to melt deposited powder to the melt pool. In figure 5, it shows that the suggested value of these two parameters for common materials in order to achieve optimal processing. Next, I will give a brief description of the microstructure of the metal powder. The microstructure of the bottom, middle, and top ends parts are illustrated in figure 6. The mechanical strength of the printed parts depends on the feature of microstructure. Due to the fact that the heat is built up in the central layer, the micro hardness here is lower than the initial and last layer. Moving on to our last step of manufacturing. After considering all the variables and parameters above, the setting of the system should be at its optimal manufacturing status. As you can see on the right, it is the model of CNC machine. The servo stepper models used for the extruder provide the ability to deposit metal powder in different angles with accuracy, while the long transportation belt drive ensures the ability to print large-scale parts. Therefore, the extruder is driven by the CNC machine, guided by the CAD and slicing model of the aircraft wings. After the machine done the printing work and wait for the molten metals to solidify, the aircraft wings production is complete. Indeed, the size limit problem and the inability of printing structural components of other 3D printing methods could be addressed by the proposed large-scale DED method. However, there are still some limitations for the method. First is the residual stress of the printed part. It is one of the sheer limitations of additive manufacturing, which can cause further damage of the printed part by material distortion and cracking. One potential solution is to analyze the thermodynamics of the DED manufacturing process as accurately as possible to minimize the presence of residual stress. Second limitation is the lack of smooth surface finish. The surface roughness of the printed part can be improved by integrating subtractive manufacturing methods to the DED system. The integrated DED system can significantly increase productivity since the transportation time between the DED workspace and the secondary machining workspace is eliminated. To conclude on our design, first of all, our proposed DED method breaks the limitation of building large parts with complex geometry, which solved the current issue in the aerospace manufacturing method. Adding on that, it also provides the high printing speed and the low material cost, and significantly reduces the lead time compared to the conventional manufacturing methods. So that's all. Thanks for listening.